Hi, this is Michael Lawless, and in this video, I'm going to discuss the Artificial Intelligent Drug Design, or AIDD module in ADMET Predictor. The purpose of this module is to optimize compounds in order to achieve high potency at the primary target, high synthetic feasibility, and good ADMET and pharmacokinetic properties. This next slide is an overview of the AIDD workflow. First, we'll start with a data set containing target activity information. So these are compounds we downloaded from the Kimball database that contain IC50 values in the form of PIC50 for base 1 inhibition. The first step is to develop structure-activity relationships and a QSAR model to predict the activity of the compounds. This can be achieved with some of the other tools in ADMET Predictor, such as class generation, and R group analyzer, which will help you probe the SAR information in order to determine what is responsible for the activity. And we can use this within the AIDD module to restrict the chemistry space so that it's pertinent to base 1 inhibitors. I've also developed an artificial neural network ensemble model using the ADMET modeler module within ADMET Predictor to develop a model that predicts PIC50 values. Next, we need to introduce a seed molecule as the starting point for the AIDD run. So here's a simple molecule from the data set we'll use as a starting seed molecule. Then we'll generate candidates, and these molecules will be generated by applying transformations to randomly selected compounds from the current population. We also have a scaffold query, which is a required substructure for all the molecules. So once it generates a molecule, it looks at the scaffold query to make sure it meets that requirement. If not, it removes that molecule and selects another one. We also have a drug-like filter that will remove non-drug-like compounds such as acetals, Michael acceptors, etc. And this can be modified by the user to remove compounds that are undesirable. Next, we'll take those candidate compounds and we'll predict target activity using the QSAR model. You can also use external programs, for example, docking into an active site, to score the molecules. Within ADMET Predictor, we have a synthetic feasibility prediction. We can include ADMET properties such as ADMET risk and pharmacokinetic properties such as oral bioavailability. Then we use a Pareto optimization to select the best candidate molecules with the highest scores. This is an example of a Pareto front. So here we simply have two objectives that we're trying to optimize, X and Y, and the lower the value, the better. This red curve represents the compounds at the Pareto front, the first Pareto front. If you need to select more compounds, we would eliminate these and then perform the selection on the rest of the molecules. And this would be this green line here. Then we iterate. So we generate more seed molecules, score them, etc. The program is optimized so that it can generate up to 10 million molecules per 24 hours. Now I'll walk you through setting up an AIDD run. We need to highlight the row containing the seed molecule. We could also highlight many molecules if we wanted to, and those would be all used as in the starting structure pool. We then click on the AIDD icon to bring up the first dialog box for AIDD. And then we simply choose our objective functions. So we limit the number of objective functions to 5 properties. So I'm going to use synthetic difficulty, oral bioavailability, or FB. I'm also going to evaluate ADMET risk, the base 1 model that we developed. So this is the AIDD QSAR model. And then we're going to also use something called BBB risk, which was created specifically for these base 1 inhibitors to optimize the potential to penetrate the blood-brain barrier. Now, once we have these over in the optimization section, we can click on a particular property to optimize and set the capping value. Capping values are very important in artificial intelligent drug design. And the reason is that anything that is the most potent compound or the best for that Pareto front is always going to be selected, and it's going to be brought to the next round of AIDD. So if you generate a compound that is very simple to synthesize, let's say it has a synthetic difficulty of 1, then that's going to remain in the population, even though it might not have an optimal base 1 inhibition. So what we're going to do is we're going to set a capping value at 2.5, such that anything that is below 2.5 in this case gets set to 2.5, that we make more pertinent compounds for this. So I'll set that at 2.5. For the oral bioavailability, I'm going to set that at 90%. So that means anything over 90% is good enough. The ADMET risk penalty I'm going to set to 0.9. Again, anything lower will be set to this. And then for the base 1 inhibition model, I'm going to give it a PIC 50 of 10. Before I move on to the next dialog box in the AIDD workflow, I'm going to discuss computing objectives using external functions. So you would have to turn on this button, this radio button here, and then select a parameter file for an external function. And I've got a few that I set up. So this is the external function that I called, and this is associated with AutoDoc. At the top of the file, you can define a file path alias. This points to a specific directory, and within that directory, you define the path. You also define a command line argument, which is a script to run. So here it's going to run this AIDD or run autodoc.bat script, which is a simple script which simply changes directories into the working directory and then runs a program called autodoc.py. This is a script I wrote to evaluate the compounds in an active site, so document an active site. Then if we move down further, this is going to write out candidates.smiles file. So when AIDD generates candidate structures in an iteration, it writes them out to this file. And then the script, the autodoc.py script, will read this, convert the compounds to 3D, doc them, and then return scores in an autodoc_.txt file that AIDD will read, and that will contain the autodoc scores for the program. So the program would allow that to execute, read in the scores, and then use that as an objective function. So now I'm going to click the next button to go to the next dialog box, and here's where you set up some filtering rules. So the first thing you can do is define a scaffold query. This can either be a smart string that you just type in here or load from a file. If you click on the MedChem Designer dialog button, it'll bring up the query structure here. And then you could modify this, maybe remove some atoms here. You can also specify that this atom is, the substituent count is drawn, so it won't create any substituents coming off this ring, etc. In this particular example, I'm going to load a smarts file called base1 scaffold query. And this is a smart string that defines the scaffold that we want to keep. So it includes this NH2 group. This is the exocyclic NH2 group in this oxazine ring, then connected to a carbon going around here. So that specifies a query. And anytime a candidate molecule is generated, it checks this smarts string. And if it doesn't match it, it throws that compound out and generates another compound. Then down here, we can define a product filter. And we've got an example of this in the ADMET Predictor tree. I'm going to use a specific one from my AIDD that I've set up specifically for this tutorial. And this is a drug-like scaffold here. And you're welcome to take a look at that file as part of the tutorials here. And this is just a list of substructures. Again, if it generates a compound, it evaluates this query file. And if it matches any of the queries in there, that compound will fail and will be replaced with another compound. So then I'll simply click Next. This is the final dialog box. Here we can specify transform rules. And there are specific transform rules set up with this particular file, but we can replace that with our own user file. We can also take a look at the transforms here by clicking on this button, and it will list individual transforms. You can turn off or on some of these transforms and then save that to a file such that you can just load that file and it will remove certain transforms. So if I click here, load from file, again, I'm going to get this from the ADMET Predictor tutorial, and these will be disabled transforms. So when I click that, you see, for example, create rings is turned off and add fused rings is also turned off in this particular example. The number of optimization runs is set by default to 100. I'm going to set it to 5 so that we can quickly produce these and we can look at the output. By default, it generates 500 compounds per generation, except for the first generation in which it will generate 1,000 molecules. And then the minimum size of the population after each pruning set is set up to 500. This is a way to increase the population initially and have more molecules to select from. We're going to set the intermediate file frequency to 10%. So that means that when reached 10% of the optimization runs, it's going to output a file containing those molecules and their predictions. We're going to use multi-threading for everything throughout, and then we need to set up a result folder. So I'll browse to a specific folder here, and that's where all the output files will be created. I'm going to a specific folder, and I'm going to create a new folder. We'll just call it AIDD-1. And then if I click that in there, it will select it down here, and all our output files will go in there. And then we're simply ready to run. So I'll click the Run button, and this will initiate the AIDD run. So it generated 1,000 molecules. Now it's evaluating ADMET risk and all the objective functions there, and then evaluating which ones we need to keep for the next population. Here it grows the population to 28. Then it has all those in the pool, so it's going to modify those, come up with a new list, predict the properties for them, and then apply the Pareto front and carry those to the next iteration, and so on. So it's going to do 5 iterations. Now it's finished with the 5th iteration, and it's generating the final population, and those will be displayed in a new window, or a new ADMET Predictor window here. So I'm going to just hide that. And you see then now we have all the objective functions here by default. And I'm just going to use View Resize Rows to fit all cell data. So that'll take a second. It's resizing all the rows so that we can see this header information and also the values within there. So let's look at this. We have the oral bioavailability, the base 1 objective function, ADMET risk, BBB risk, and synthetic difficulty. And let's just sort this in ascending order. And you see some of these are negative. A negative PIC 50 value doesn't make any sense, but what it's done is this particular compound is out of scope for the base 1 model. It penalizes it by 10. So it takes the calculated PIC 50 value and subtracts 10 from it. So the predicted IC 50 value is around 4. Subtract 10, it gives it a negative value. And this is a way to penalize compounds that are out of scope of the model. If we sort in the other way, we see that the highest scoring molecule has a score of 9.3. So this would be a sub-nanomolar predicted compound here. Now let's just reset that to the original values. And let's look at the spreadsheet controls here. When it creates this file, it automatically sets up the filtering here. And this allows you to filter out compounds based on their property. The oral bioavailability ranges from about 5% to 90%. So we want to throw out compounds, let's say, that are below 75% oral bioavailability. And then when we hit the tab, this has filtered those compounds out. It's filtered out 20 compounds or hidden those 20 compounds here. Now for the base 1 model, let's set that to, let's say, 8.1. And again, it filtered out a few more compounds, this time about 230. For ADMET risk, the lower the value, the better. And you see we've hit the capping value of 0.9 for a lot of these. So let's go with the value of 1 here. And that filters it out to about 17 molecules remaining. So maybe we can go a little bit higher. If we go to 2, now we have 95 compounds left. And then for the BBB risk, let's set that to 1. And now we have 73 compounds, which we could select for further optimization. Here you might want to go through this list with your chemist and see which ones they think they can synthesize. Then you would synthesize these and then improve your QSAR model. So you get the PIC50 values from that, change your IC50, change the model, and then do another run of artificial intelligent drug design. You also may want to modify the drug-like filter to throw out any compounds that are generated that just seem undrug-like. Maybe they're unsynthesizable. Maybe you don't like more than one halogen in here, so you could eliminate compounds with, say, 2 chlorines or 2 bromines or a chlorine and a bromine, etc. It is an iterative process, and it's important to talk to the chemist and get their feedback on what's synthesizable. And you can then modify the inputs to AIDD to be more selective about what hits are obtained. Before we finish this video, I'd just like to discuss some of the output files that are placed in the folder. So the first one is the AIDD run.log file. And this contains the setup, so your objective functions, the capping values, whether you're minimizing or maximizing that property. It also lists your out-of-scope penalties, so the standard model is 10. This was applied to the base 1 IC50 model for out-of-scope predictions, pH dependent, etc. It also lists your scaffold query, then the file for the query file. So this is the drug-like properties folder here, or file, the transforms that were used, the generations, and then each number of molecules per generation, and then the number of new molecules added to the pool. There's also files here for intermediate results. So let's take a look at one of those briefly. So this is on the final iteration. It's going to contain the SMILES, the ID, what generation that particular molecule was created in, the number of reactions to get to that, all of the objective functions for each one of this, and then the reactions here. So this is a list of the transforms that were applied to create this molecule. And those transforms are listed in this molecular transforms file so that you can go back and kind of figure out what transforms were used to create that particular molecule, and they're listed in here. Thanks for watching, and if you have any questions, please email. Take care, and I'll see you next time. Bye-bye.